Welcome to Ask and Learn.
We want to sketch the graph of x minus 1 squared over x squared plus 1. Now, normally when we are wanting to graph a rational function, one good thing to do is to go ahead and factor everything, and we already have it in factored form, since x squared plus 1 does not factor over the real number, so we don't need to worry about factoring that one. And now all we need to do is follow that laundry list of steps that is listed in this chapter for us to be able to actually graph this. So the first thing they tell us to do is to look for our domain. And the only issues we would have with a rational function is where our denominator is equal to 0, but x squared plus 1 will always be greater than or equal to 1, so our domain ends up just being all real numbers. Now we can go ahead and look for our intercepts. So let's first find our y-intercept. So y-intercept is where x is equal to 0. So doing that, we're going to end up getting 0 minus 1 squared over 0 squared plus 1. This is equal to y. So 0 minus 1 is negative 1. Squared is 1. So we're going to have 1 over 1, which is just 1. So y is equal to 1 will be our y-intercept. And we can go ahead and find our x-intercept too. So x-intercept, well, this is when y is equal to 0. So I have x minus 1 squared over x squared plus 1. Now we will just set our numerator equal to 0, since no matter what we plug into the denominator, we can never make the whole function equal 0, which would just tell us 0 is equal to x minus 1 or x is equal to 1. Next thing they want us to do is to determine if this function has symmetry. So rational functions are normally not known for being periodic, so we don't have to worry about that. But we can check to see if this is an even or odd function for symmetry about the y-axis or the origin. All right, so we'll look at f of negative x, and plugging that in, we'll get negative x minus 1 squared all over negative x squared plus 1. And we can factor that negative 1 out, and then squaring that negative 1, we just get x plus 1 squared over x squared plus 1. And this here is not equal to f of x, nor is equal to negative f of x. So what this tells us is no symmetry, or at least no symmetry about the y-axis or about the origin. Next, what we want to do is to find our asymptotes. So we at least know we're not going to have any vertical asymptotes, since our denominator can never equal to 0. So we can go ahead and look at our end behavior of this function as it goes to infinity and negative infinity, and we know it's going to have the same behavior on each side due to the fact that in the numerator we have a power of x squared, and in the denominator we have a power of x squared for the largest powers. So all we need to do is to take the coefficients from each and divide them. So in the numerator, if we were to FOIL that out, it would be just x squared. So leading coefficient of that is 1. And the leading coefficient in the denominator is 1 also. So we have a horizontal asymptote at y is equal to 1. Or at the line y is equal to 1, I should say. The next thing we want to find are our intervals of increasing and decreasing, and we want to find any local max or mins. And so these are steps 5 and 6, but I'm going to go ahead and do them in one step since these do go together. Next, we want to find what y prime is and able to answer where it is increasing and decreasing. So let's go ahead and do that on a new page. So So y prime is equal to x minus 1 squared over x squared plus 1. Ooh, not y prime, that's just y. Right, so now to take the derivative of this, we're going to need to use the quotient rule. So quotient rule says low d high minus high d low all over the square of what is below. So x squared plus 1. We're going to square that. Now, to take the derivative of x minus 1 squared, we're going to need to use chain rule and power rule. So power rule says move that 2 out front, and we'll have that times x minus 1. And then we would need to take the derivative of the inside of x minus 1, which would just be 1. And now to take the derivative of x squared plus 1, well, that's going to be 2x for x squared, and the derivative of 1 is just 1. All right, now if we were to go ahead and do all that algebra and simplify and do a little bit of factoring, we'll end up with 2x squared minus 1 over x squared plus 1 squared for y prime. And we can go ahead and find what our critical values are going to be. So that just implies that x squared minus 1 is equal to 0, or x is equal to plus or minus 1. So we know possible maxes and mins at x is equal to plus or minus 1, and we also know y prime. All right, so let's go ahead and write that down now. So y prime is 2x minus, or x squared minus 1 all over x squared plus 1 squared. Now we want to find where the function is increasing first. And this is where y prime is strictly greater than 0. So going through the algebra for that, we will end up with that this is the interval -1 to -1 union 1 to infinity. And then we can find where the function is decreasing by looking for where this function is strictly less than 0. And it's just going to be our remaining intervals here, which is going to be -1 to 1. Now we had those critical points where x is equal to -1 and x is equal to 1. So let's go ahead and use the first derivative test to see if these are maxes or mins. So between -1 and 1, the function will be decreasing, and to the left of -1, it will be increasing, and after 1, it'll be increasing. So that tells us x is equal to -1 will be a local max. So local max, and this will tell us x is equal to 1 will be a local min. Then the next thing we want to do is to look at the concavity of the function and look for any points of inflection. So we're going to need to know what y double prime is for this. So to find y double prime, we're going to need to use the quotient rule again. So first thing I'm going to do is factor out that 2. And now we can just go ahead and write everything. So it's going to be low d high. And just to kind of save some space, I'm just going to go ahead and take the derivative of x squared minus 1, which will just be 2x. Wrong color. So 2x. And then minus high d low. And the derivative of our denominator, we're going to have to use chain rule and quotient rule again. I mean, chain rule and power rule. So it's going to be 2x squared plus 1 times the derivative of our inside function, which is going to be 2x. Then we're going to need to square whatever we have in the denominator. So it was squared before, now it's going to be to the fourth power. And now if we were to do all that algebra, we can simplify this down to negative 4 x times x squared minus 3 all over x squared plus 1 cubed. Now we want to set this equal to 0. And so we only need to set the numerator equal to 0 again. So we get x is equal to 0, or x squared minus 3 is equal to 0 by the zero product property. And we would get from this that x is equal to plus or minus the square root of 3, which is approximately equal to plus or minus 1.73. Right, so now we can go ahead and figure out where it's concave down, concave up, and we can determine if those points we listed are actual points of inflection or not. So we have negative 4x squared minus 3 all over x squared plus 1 cubed, or y prime. Now it's going to be concave up when y double prime is strictly larger than 0. And that is going to be the interval negative infinity to the negative square root of 3, unioned with 0 to the square root of 3. Then it's going to be concave down when y double prime is strictly less than 0. And it will just be the rest of the interval. So negative square root of 3 to the square root of 3, or to 0. And then union square root of 3 to infinity. So we had x is equal to negative square root of 3, x is equal to 0, and x is equal to the square root of 3. So we know the function will be concave up to the left of the negative square root of 3, and also between 0 and the square root of 3. And on the other interval is going to be concave down. So at each of these values, we do have a change in concavity. So all of these will be points of inflection. Now let me go ahead and zoom out a little bit. And this was the last thing that they said we should go about doing before we start graphing. So let's go ahead and plot some of the points we know already, and then maybe decide if we need to plot some more. All right, so we have the point 0, 0, or not the point 0, 0, but x is equal to 1 as our intercept. And our y-intercept is going to be 0, 1. So we have those 2 points that we can plot. We know we're going to have a horizontal asymptote at y is equal to 1. We know at x is equal to negative 1, we're going to have a local max. So I'm just going to put max below this. And at x is equal to 1, we're going to have a minimum. So we know that this here will be a minimum point. We also are going to need to use our points of inflection. So this is going to be negative square root of 3, and over here will be square root of 3. And so we know at those points, our graph should kind of flatten out a little bit and change concavity. All right, so actually maybe I shouldn't put those because we don't know if we're going to be above or below the horizontal asymptote yet. All right, so let's just go ahead and start with this. Now, let's start from our y-intercept. We know that we're going to start there and go ahead and go to our x-intercept. So we're going to go ahead and touch that, and we know this is going to be a local minimum, so we should go ahead and bounce up afterwards until we hit the square root of 3, and then it's going to change concavity. So we're going to approach our horizontal asymptote from the bottom as we go to infinity. Now, for y is equal to, or x is equal to 0, on that interval, we know the function should be decreasing. So that means after this point, it should be going up until we reach our maximum at x is equal to -1. And then it's going to keep on going until we hit negative square root of 3, where concavity will change. And at that point there, we will approach our horizontal asymptote from above. So we actually didn't need to go ahead and plot any more points, but sometimes it's nice to go ahead and say what this max is, and maybe even the points of inflection, what values those are supposed to be. But since we're just trying to sketch it, I think this is good enough for what we're trying to do.